Okay, so this is a question from the June 2013 paper, and it's all about AC current. So let's take a look at the first question. So it says state the peak-to-peak voltage. Now quite a lot of people get confused when they're asked peak-to-peak, because they end up drawing something that looks a bit like the wavelength for other waves. But that's not what peak-to-peak voltage is. Peak-to-peak voltage is a vertical distance, and it's the distance between the highest peak and the lowest trough, like this. So to calculate what that value is about minus 64. It goes up to plus 64. So that must mean your peak-to-peak voltage is 2 times 64, which equals 128 volts. So the next part asks you for the peak voltage. So the peak voltage is just the distance between your centre line and the top of the peak. And obviously, having measured that before, it's going to be 64 volts. Useful way to check, this should be exactly half of your peak-to-peak value, which obviously it is in this case. The next question asks you to calculate the root mean square of the voltage. So this is I'm going to need you to remember your equations. So the VRMS is equal to the V peak divided by root 2, which in this case is equal to 64 by root 2, which equals 45.3. Let's see, that's the unit volts there. So looking at this waveform, you're asked to calculate what the frequency is. So the frequency is obviously the number of cycles per second. So what you need to do from this question is calculate the time it takes for one cycle, and then you can convert that into the number that you can have in an actual second. So the time it takes for one cycle is effectively like measuring the wavelength on the oscilloscope here. So you're looking at this distance here, and obviously you can see in this one the time period is 10 milliseconds. Okay, let's bear that in mind going to this bit. So it takes 10 milliseconds to do one waveform. We want to know how many you can get in a second, so because that's what the frequency is. So frequency would be 1 second divided by the time for one waveform, so that's 10 times 10 to the minus 3, which should give you an answer of 100, and we measure frequency in hertz. So this next part asks you to show the DC voltage that gives the same rate of energy dissipation. So what you're looking at is the DC equivalent voltage, and that is the same as the root mean square voltage. It's just different ways of talking about the same thing. The DC voltage that gives the same rate of energy dissipation is the RMS voltage, or the root mean square voltage. Obviously we previously calculated that was 45 volts. So let's draw in a line at the 45. That's around about here. It's a bit difficult to do a straight line on this, but it's a bit wonky, but you can do this with a ruler on paper. And as you can see, it's DC, so it's a continuous, it's like straight horizontal line all the way across at the level we calculated for the root mean square earlier. And that's what it's looking for here. So this next question's testing your knowledge of the working functions of your oscilloscope. So it tells you your oscilloscope has 8 vertical and 10 horizontal divisions to work with, and you need to set up the oscilloscope to display the alternating waveform so that the 2 complete cycles are visible. So let's move that up to give ourselves some space. So the first thing you need to do is that if you want to connect or display a waveform on your oscilloscope, what you need to do is you need to connect your waveform generator to the Y inputs. So then, if say your waveform is generating a voltage, that will display your voltage on the Y-axis of your oscilloscope. So you connect that to the Y input, and it's usually important to have this. I would reckon this would be a keyword in the answer to this. Now the next key part is it tells you that you need 2 complete cycles visible on your oscilloscope. So from the previous question we calculated that one waveform was 10 milliseconds. So obviously that means that 2 waves are 20 milliseconds because it's twice as long. Now it tells you you've got 10 horizontal divisions to display that over. So one division would have to be 20 milliseconds divided by 10 equals 2 milliseconds. Now the gain settings, which you would turn on when you adjust when you are using your oscilloscope, tell you the number of milliseconds per division. So the gain setting you have to put it on to enable you to display 2 complete wavelengths would be 2 milliseconds per division. So that's dealing with in the X direction across the screen. But what about in the Y direction? Because earlier on we measured the peak-to-peak value of it, and we got the peak-to-peak was 128 volts. So we want to be able to display that on your screen, and obviously we've got 8 vertical divisions in to do that. So one division would be equal to 128 divided by 8 divisions, which gives you 16 volts. So that your Y gain will be 16 volts per division to fit onto the screen. So you've got your Y gain of 16 volts per division to fit it onto the screen, and also you've got your X gain, which we calculated as the 2 milliseconds on it. And those are the key things you'd need to get the marks on this question.